Good afternoon. I was expecting something louder than that. I guess it's end of the day, but this is the beginning of the day for me. So good afternoon. Yeah, that's better. So thank you for inviting me. It's been very interesting looking around and discussing about some of the opportunities that you guys are working on. So today I'm going to be talking about decision support tools for infrastructure resiliency and security. As you were just told, I'm with Oak Ridge National Lab, and Oak Ridge National Lab is a Department of Energy laboratory. So because of that, most of what we do support the Department of Energy mission. So what I plan to talk to you about when I was told to give this talk on decision support tool, I know that you've had great classes about some of the specific algorithm and things like that. But when we talk of critical infrastructure and interdependency, so there are some salient points that actually drive some of those algorithms that you may be developing or you may be using. So what I plan to do is to actually expose you to some of those within this framework. So the outline that I'm going to be talking about is talk a little bit about the complexity of critical infrastructure network. And to do that, I'm going to be focusing more on the United States rail network. So, and I will give you some of my reasons for that. Then talk about decision support tool for multi-stakeholders. Basically, when you have to develop decision support tool for various agencies. Describe briefly one particular decision support tool that we developed for transportation routing analysis. So that is just one thing, but when, for my public lecture, I'm going to actually talk a little more about some other decision support tools, right? So we all use some of these tools, even though they are so common that we don't realize how they influence our decisions, right? But even if you look at the weather app, even though it's so basic, the algorithm that actually drives it is very complicated. That algorithm actually uses supercomputer. And this bring out the output to you, and they give you all these temperature values by time, and you just look at it and you think, oh, that's good. The weather is going to be great today. But that is extensive amount of computation that drives it. And not only that, it also has a lot of assumptions behind it. So one can then say that decision support tools help users to make effective decisions. And you can have decision support tool in various forms, right? So I was talking about the weather app. That is something that actually are used by everybody globally. So in designing such a tool, you have to assume that what are people going to need from it? So you design it in such a way that it appeal or it meet that need. So they also help us to facilitate effective management, actually. In this case, you may need to generate a lot of evidence-based decisions. So you have to follow that and then come up with understanding of, okay, what evidence am I deriving from this to understand what I should do? So I talked about the app, which is a dynamic software, but decision support tool can also be information system. So it can be a system collecting data, and you are querying the data to get insight about what is going on. Developing an app tool and a weather app for use is very basic in terms of the users. But developing a decision support tool for critical infrastructure system is not that simple. It's a complex phenomenon. And what we plan to do is to review some of those complexity. So I mentioned that in this talk, I'm going to focus on freight transportation in the US. So how many critical infrastructures do we have? Anybody? 16 sectors, 16 critical infrastructure sectors. So can anybody name one of them? Wastewater, okay. Another one? Transportation. Your professors are doing the answering. Anybody? Electricity, very good. Any other? Natural gas, okay. Communication system. So there are 16 of these. So those are critical infrastructure sector. And why are they called critical infrastructures? They are critical infrastructure because they are the lifeline of any society, right? So imagine today if there is no electricity. So picture your apartment or your house right now, and imagine everything that you have in that apartment or that house. And imagine there is a loss of electricity. Tell me which of those gadgets or electronics that you have will actually function. Probably none of them. The cell phone will function for some time, but after that, then you may lose cell phone services as well, right? So those are critical infrastructure that we rely on. So transportation is one of those, right? And freight transportation is a key component of that. Why is it a key component? Every year, over 20 billion tons of goods were moved around the United States. And those are moved on rail network, highway network, and waterway. In addition to that, we have all these multi-jurisdictional components. So for example, within DOT, which is Department of Transportation, we have all these many jurisdictions. Those are individual agencies that manages sectors or portion or segment of the transportation network. And they have their own regulatory requirements. And if you go to other areas, we have state, like state of Oklahoma, and we have municipalities that also have their own jurisdictional requirements. So when you are transporting freight across multi-states, you have to follow some of these. And those are some of the things that influence how you design a decision support tool. So the stakeholders are both public and private. So public from the government side, private from the owners of some of these assets. So that is for freight transportation as a whole, which can include so many things. But one aspect of that freight transportation is the transportation of spent nuclear fuel. So spent nuclear fuel are waste from nuclear power plants. And it's the responsibility of the Department of Transportation to actually move this waste across the state, so to a permanent depository. And to do that, they can take it over the road network, the rail network, or even waterways. And as I mentioned, those are controlled by geographic and other laws that may impact how they do that. So just to give you a background into spent nuclear fuel. So we have about 104 nuclear power plants all over the country. And here on this map are where those are located. So that is a picture of one of the nuclear power plants. And once they use radioactive material, and after it is used, they need to transport it. Although it doesn't have enough radioactive content in it to meet their requirement for nuclear power plant, but it's dangerous enough that it can be used for things like dirty bombs. So because of that, they have to protect the waste. And to protect those, they usually put them in storage like this. These are concrete cast. And after being put there, they need to move them to a location where they can actually store them. And to move them to those locations, this is a schematic of the supply chain network. So this is from the origin site to the destination site. And you can see from here that it can go, if it goes on water, those are the organizations that are actually responsible for managing or monitoring that movement. On rail is another set of organizations, and on the road is another set of agencies that is monitoring that. So this is another way to look at it. So from the origination point, those are owned by utility companies. And utility companies are private sectors. Then it can go on truck, which is just to move them from the point of origin to where they can be put on rail. So those are managed by different private sectors because it can go on truck, railroad, or even barges. Then after that, you have to preload it. So that's another set of movement. Then before you transport it to the depository. So this schematic is the supply chain schematic for if you are moving it from point A to point B within the United States. If you have to move it outside the United States, then you have a different set of supply chain network. So in terms of agencies, these are the agency abbreviations that are responsible for each stage. So from the shutdown side, we have the Nuclear Regulatory Commission, we have the Department of Energy, and we have the state of origin. Then you go to modal transportation, and you have all that agencies. In addition to all these agencies, you also have these overlaying regulatory requirements. So these are code for federal regulations, and those are the numbers. So those regulations actually tell you specifically what you should do as you move from one point to another. So before I go into some of the actual routing algorithm that one can use, just want to give you some background into railroad basic. So most people usually don't think of railroads when we talk about transportation. We think mostly of highway, and in some cases, waterway. In fact, some people may even say that railroad is a dying mode of transportation, but that is not very true. Railroad is actually used for some of the critical transportation of critical assets. So because they have some unique characteristics. And if you look at the network, this is a map that actually depicts all the rail network in the United States. So the lines are individual links, and the purple dots are the individual nodes, which are rail yards that you can actually use to transfer from one rail network to another. So some of the characteristic feature of this is that there are about 500 rail companies in the United States. So all the network that I show you are owned by private sectors. None of those is owned by the government. So if you are government, state or federal, and you are responsible for transporting something, and you have a network that is owned by the private sectors, then that is very complicated because you have to determine how to effectively do that. In addition to that, there are rail companies that only have very short line. We call them short line, which is about a mile. So there are others that are big network that can control most of the network, but there are some that are just in charge of a mile. So for example, if you look to the west, you can see these rail network right there. That's a single company. So if you want to move something that need to go over that, you have to take into consideration what that company actually require you to do. So as I mentioned, rail network is actually used for a lot of things. As of today, they carry approximately 30% of freight in the US, and they are mostly coal, ag products, and chemicals. So there is another thing that we should know about the rail networks. When we talk about highway network, so the highway network is actually built by the government. So if you want to transport anything, all you have to do is get in your car and put the stuff in your truck and just drive, right? So for rail network, they actually have what they call trackage right. So which means that if you own a rail network, only your own train can actually go on that network. So your train cannot go on other people's network, other private sector network. For them to do that, you actually have to go into negotiation with them to incorporate their own requirements into your routing algorithm so that you can determine how to meet their need. So with all this background information about some of the requirements, there are some methodologies that are widely used for this kind of routing analysis. Optimization is the most popular, and there are several algorithms that are used, but those are better for planning analysis. Graph theory is another area that is widely used, and they have some benefits that they can actually do. GIS is another one, which is mainly used for visualization and to some extent network analysis, but you cannot do large network on using GIS analysis. So now going to the decision support tool. So the decision support tool I'm going to be talking to you about is called Trackage, so which stands for Web Transportation Routing Analysis, GIS. So the web basically means it's an online decision support tool, and it was originally developed to do routing analysis for spent nuclear fuel. But after the development, it has actually been used for other applications. So the element of this is that it is multimodal, so which means that it has a capability to do highway, rail, and waterway analysis, and it takes data from different sources. So for example, it takes road network from shapefile provided by Tiger. It takes some data from Army Corps of Engineers and FRA and others. And it has capabilities for uncapacitated network. So this is a web-based browser. And the way it is done is that you actually then take all the routing analysis. And the most important component of that is that as you are transporting nuclear waste across the network, you have to account for exposure. What level of population are you exposing as you are traveling? So the idea is to minimize the exposure using the population data set. So I guess you are familiar with routing models. So routing models basically involve a network. So you have the link and the node. In transportation, they are referred to as the node and the arc. and know that the location, such as the switch station, the origination, and the arc are basically the network you are going to be going through. So for the highway network, this is the Trackage routing based on that. So basically, it uses the popular routing idea. So it calculates the total impedance on a road. And for that, it asks components for distance as well as for time. So if you are interested in coming up with a route that is more sensitive to time, then you have to provide a weight for that. In general, within this, the alpha is 0.3 and the beta is 0.7, which means you give more weight to the distance rather than time. So in transporting the nuclear waste, you are not trying to come up with the shortest path, but you are trying to come up with the safest route, because you want to minimize the amount of, so if there is, for example, an accident, you want to minimize the exposure of the citizen to radioactive material. So that is why you count for that. Then there are some portion of the highway that are specifically designated to carry radioactive materials. So those are classified as HRCQ routing. And for those, the distance and the time is still the major thing, but you have to provide different weight to those so that you can account for using those particular network. So in this case, for example, the gamma is a non-preferred route multiplier. So if it's 1, is the preferred route. So you can set it to a very high number if it's not the preferred route. So that means you are penalizing that particular route because it's not the designated route for radioactive material. The routing model is also very similar for rail network. And the only difference in this case is that because you are going to be going through different level of rail type, so we need a way to account for different weight. So if the network is a long network, you want to remain on the long network as much as possible so that you minimize the need to transfer your goods from one network to another. So if you are going on a shorter route, you want to penalize that shorter route because you will need more frequent transfer of the waste. And material handling of the waste from one point to another so frequently is a potential risk for accident and other problems. So there is also the component of dedicated train. So I mentioned at the beginning that the rail network is mostly privately owned, and for you to go on the network, you have to use only your own train. So if you need to move your train from one point to another on another network, you have to go into negotiation with that company. And basically, you transfer your goods to their train to move on their network. But for dedicated train routing, what you are trying to do is that you actually want to use a single train to move through the entire network, irrespective of who owns the network. So, and this is commonly used for DOE designated train routing because they want to minimize transfer as much as possible. So waterway routing is another option that is incorporated in there. For waterway is a little bit different because you don't have restriction like the rail or the highway, So the water is basically open, but even though it's open, you still have some constraint that is actually limiting where you can go on the ocean. So these are some of the weighting factors that actually inform that. For example, you want to minimize at all costs going through the Great Lake, for example. And also you want to minimize going through inland waterways. Shallow inland waterways is another reason. So with that, this is just some snapshot of what the tool actually look like. So it has some control menu that we allow you to do some of these analysis. So this is what the tool looks like. So at the top here are the various mode that you can select. So for example, if you want to use the railroad, and immediately that is selected, you have to identify the state of origin. So let's pick California. Then within the state of California, there are different companies that you can actually select that's going to do the initial transportation. So if you change the state, that will actually change as well. So let me see. Let me start audio. So you pick the company, I mean the node that you are transporting from, and then you select the company. So in this case, for that particular node, there is only one company. So if I select another node, there is also a single company. So you select that company. So in that case, you definitely don't have any other choice than to go with that company. And then you can select the destination state, and you basically repeat this process for that as well. So in this case, we have 3 companies that are viable for that particular node. So you select the one of choice. Then here you want to select whether you want to use the dedicated train or not. So that is what the decision you make. Then at this portion is what we call the route options. So basically you want to say, I want to block some state. So if you want to transport across state, but you don't want it to go through a particular state, maybe because of some additional regulations, so you don't want to incur the cost of meeting those regulations, so you can actually block those states off, then it will take that into consideration. So let's say we want to block off certain state. Then once that is done, then you run the algorithm. So then it gives you the route based on all those selections. And here, there are a lot of options you can actually look at in terms of downloading the output. So for example, you can show things like tribal lands. So I want to see the location or the location of this route with respect to any tribal lands. So if you select that, that data set should pop up and you can see what is the relative distance to those. You can identify, you want to know which counties those actually go through. And these are other critical infrastructure that you want to use to further evaluate the route. For example, nursing home, hospitals, daycare center, fire station. Fire station may be one that is very important, that in case of accident, I want to know if somebody can respond quickly. Of course, there are so many of those. So, but what you want to do later on is actually to say, okay, I want to see fire station within 5 miles of that route, something like that. Then there is the highway that is shown. Then population is another option where you actually can overlay the population data and see what that means for the route. You can download this and then use in another, maybe another decision support tool or for further analysis, or to even hand out to your drivers so that they will know the specific route to follow. So this is what I just showed, some of the slides for that. So I talked about if you want to block a particular state, so that is, and you can do that by drawing a box on the map itself or by selecting from the list. And this is just showing the output. And here is also showing some of the route method. So you can select depending on what type of mode. So in this case, it's highway. So you can select additional route method. So whether it's commercial or you for ASMAT or other. And also in this case, you can select things like how many drivers are actually going to be driving. That is important because there are also regulations about how long one driver can actually can drive continuously. So when you select that, it will actually take that into consideration as a constraint. And then, so that will be different if you select 2 versus 1. Then maximum speed is another one. Basically, it dictates, it depends on what type of freight you are transporting. So if you are transporting nuclear waste, for example, there are stipulated maximum speed that you can go. So, and that has to be integrated as well. So these are the options for the rail network. And this is for the waterways. So the pop-up of the options that you actually get, it all depends on what you select at the top as the mode of transportation. So these are just some examples just to show. So this is for a rail route. This is for a dedicated train route for the same problem. So you can see that there is a little bit of difference between those. And then this is for the waterway. So this is actually a case study that was implemented with specific locations in mind and type of material. So this was from Crystal River in Florida, and we did the type of reactor selected and other information. So in this case, they were actually trying to remove nuclear waste from Savannah River, from that Crystal River, from Crystal River, Florida, to Savannah River site in South Carolina. So this is scenario 1 that actually use highway, but use the highway route control quantity, which are designated roads. And this is another route using the rail network that actually compared, you can then compare those two. So, but in this case, DOE preference is actually to use the train. So this will be the preferred option if they are transporting nuclear waste facility. And of course, if they are using the waterway, so this is what the route is going to look like for for domestic transport as well as for international transport. So in summary, what I try to bring to your attention is the fact that in developing decision support tool, it's not sufficient just to look at the basic problem that, okay, I want to get, for example, in routing, I want to get things from point A to point B. But you have to also look at the other component that actually detect what that should look like. So, and those actually have more stringent requirement than the routing analysis itself. So those are the things that actually provide some constraint that may make the routing algorithm even more complicated. And so understanding the geography of different regulatory and stakeholders and performance requirements is key. So I mentioned at the beginning that if we are developing a weather hub for everybody, you don't need to know who those people are. You just need to say, what would they like to get from this? And then you design the tool to meet that basic function. And people will adapt to it. But in cases like this, you actually need to know what the institutional requirements are before you can actually go into designing your decision support tool. And finally is that modeling the multi-layer interdependency. So when we talk about interdependency, in analysis we think mostly of the physical interdependency, but what I've just talked about is actually looking at the logical interdependency, the requirements and the various requirements that is actually influencing what you are supposed to do. Those are things that you don't see, but they are on the book that controls you. So I just need to acknowledge these two people as part of the team that work on Web Trackage. With that, I will take your questions.